There is a world in our solar system that appears in every astronomy textbook. Its rings have inspired artists for centuries. Children draw it in school projects. Adults point telescopes at it on clear nights. Saturn represents something romantic about space exploration, a destination that feels both familiar and exotic, close enough to photograph in stunning detail, yet far enough to remain mysterious. But there is a fundamental problem with Saturn that most people never consider. It is not simply far away. It is so far away, and the physics of reaching it are so demanding, that a human journey there would almost certainly be permanent. Not permanent by choice, permanent because the laws of physics would make returning essentially impossible. Before we can understand why Saturn represents such an absolute barrier, we need to grasp the scale of distance involved. And this is where human intuition fails completely. Saturn orbits the Sun at an average distance of 886 million miles. That number is so large that our brains refuse to process it meaningfully. Here is one way to make it tangible. When you observe Saturn through a telescope tonight, you're not seeing the planet as it exists at this moment. You are seeing light that left Saturn roughly 80 minutes ago. A radio signal sent from Earth takes over an hour to reach the planet, and another hour for any response to return. If you could somehow drive a car to Saturn at highway speeds, say 62 miles per hour, without ever stopping, the journey would take over 1,600 years. That is longer than the time between the fall of the Roman Empire and today. Generations would live and die behind the wheel, and their distant descendants would still be driving. Consider Mars, the planet that dominates our current ambitions for human exploration. At its closest approach, Mars sits roughly 34 million miles from Earth. Saturn is approximately 25 times farther. Every challenge we face sending humans to Mars, the radiation exposure, the psychological isolation, the supply logistics, the equipment reliability, must be multiplied by a factor of 25 when considering Saturn. And then new problems emerge that we have not yet begun to solve. A journey to Mars takes approximately 6 to 9 months using conventional propulsion with favorable planetary alignment. A journey to Saturn using the same technology would require 6 to 7 years one way. 7 years inside a spacecraft, 7 years of recycled air and recycled water, 7 years of watching Earth shrink from a blue marble to an invisible point lost among countless stars. And that is merely the transit, before any of the real problems begin. Distance alone does not make Saturn unreachable. The real barrier is energy. Reaching Saturn requires an enormous amount of fuel. But here is where the mathematics of space travel become unforgiving. Every kilogram of fuel a spacecraft carries needs additional fuel to accelerate it. And that additional fuel requires even more fuel to move its own mass. This relationship is described by the Tsiolkovsky rocket equation, and it is one of the most punishing constraints in physics. To accelerate a spacecraft to the velocities necessary for a reasonable Saturn transit, and then slow it down enough to enter orbit rather than flying past, requires fuel quantities that quickly become absurd. The numbers break down so badly that engineers had to invent a completely different approach. That approach is called gravity assist. Instead of carrying enough fuel to reach Saturn directly, spacecraft use the gravitational pull of other planets as free acceleration. The Cassini probe, launched in 1997, did not arrive at Saturn until 2004. 7 years of carefully planned trajectories, swinging past Venus twice, Earth once, and Jupiter once, stealing small amounts of momentum from each encounter to build up the velocity needed for the outer solar system. And Cassini was an unmanned probe with a total mass of approximately 12,300 pounds. A crewed mission would need to be orders of magnitude heavier. life support systems, food supplies for years, water recycling equipment, radiation shielding, living quarters, exercise facilities, medical equipment, spare parts for every critical system. The more mass you attempt to move, the more fuel you require. The more fuel you carry, the more mass you have. It is a spiral that has no clean solution with current technology. Assume for a moment that propulsion technology advances enough to make the journey feasible. The next barrier is radiation. Astronauts aboard the International Space Station operate within Earth's protective magnetic field. They receive elevated radiation exposure compared to people on the surface, but the levels remain manageable. ISS astronauts absorb approximately 150 millisieverts of radiation per year, roughly 50 times more than average ground-level exposure, but within acceptable limits for career astronauts. Beyond Earth's magnetosphere, those numbers change dramatically. On a journey to Saturn, astronauts would be exposed to galactic cosmic rays and other particle events with minimal shielding. Estimated exposure levels reach 600 to 1,000 millisieverts per year. Over a 7-year transit, cumulative exposure would reach 4,000 to 7,000 millisieverts. For context, NASA's current career radiation limit for astronauts is 1,000 millisieverts total. A single trip to Saturn would exceed that limit 4 to 7 times over. The biological consequences are severe. DNA damage accumulates faster than the body can repair it. Cancer risk increases substantially. Perhaps most concerning, research indicates that cosmic radiation causes measurable cognitive decline, degradation of memory, decision-making ability, and reaction time. There is no practical shielding solution with current materials. The particles involved are so energetic that stopping them requires enormous mass. Worse, thick shielding can actually increase secondary radiation when high-energy particles strike it and fragment into additional harmful particles. Radiation is not the only assault on the human body during a Saturn transit. Microgravity itself becomes destructive over these timescales. ISS astronauts spend approximately 6 months in orbit. Even with 2 hours of daily exercise, they return to Earth with measurable bone loss, muscle atrophy, and cardiovascular deconditioning. Some never fully recover their pre-flight bone density. A Saturn mission means years of weightlessness, not months, years. Bones lose density at roughly 1 to 2% per month in microgravity. After 7 years, bone loss could potentially exceed 80%. The skeleton would become so fragile that ordinary movements could cause fractures. Standing in any significant gravitational field would be impossible. Muscles follow a similar pattern of deterioration. The heart, a muscle itself, begins to shrink and weaken without gravity requiring it to pump blood against resistance. After years in space, it would struggle to maintain adequate blood pressure in any gravitational environment. Vision deteriorates as fluid pressure changes in the skull. Balance systems designed to function with gravity become confused and eventually non-functional. The immune system weakens. Dormant viruses reactivate. Wounds heal more slowly. After 7 years of transit, the human body would be fundamentally transformed, and not in ways that permit normal function upon arrival. The obvious solution would be artificial gravity, a rotating spacecraft that simulates Earth's gravitational pull through centrifugal force. In theory, this works. In practice, the engineering requirements are staggering. To generate comfortable artificial gravity without inducing motion sickness from rotational effects, a spacecraft would need a rotation radius of at least 330 feet, spinning at a precise rate. Building such a structure, launching it, and maintaining it for a decade-long mission exceeds current engineering capabilities. The mass requirements alone would compound the fuel problem exponentially. And even if such a spacecraft could be built, it would still need to function flawlessly for nearly 10 years in deep space, with no possibility of resupply, and no possibility of repair from Earth. A single critical failure would not result in rescue. It would result in death. Everything discussed so far assumes the goal is simply reaching Saturn, surviving the transit and entering orbit. We've not yet addressed what happens upon arrival. Saturn has no solid surface. It is a gas giant, a world of hydrogen and helium that becomes progressively denser and hotter with depth until pressures and temperatures crush and vaporize anything we could conceivably build. You cannot land on Saturn. You cannot even descend into its atmosphere without being destroyed. The realistic mission goal would be to orbit Saturn and study its remarkable moons. Titan, with its thick nitrogen atmosphere and liquid methane lakes. Enceladus, with its geysers of water ice suggesting a subsurface ocean. These destinations hold genuine scientific interest. But even orbital operations present the same fundamental problem. Eventually, the mission must end, and ending means coming home. The return journey is where the mathematics become truly impossible. To leave Saturn's gravitational influence and accelerate back toward Earth requires enormous amounts of fuel. But remember the rocket equation. Every kilogram of return fuel must be carried from Earth at the mission's start, which means carrying additional fuel to move that fuel, which means carrying even more fuel to move that additional fuel. A round trip to Saturn requires fuel for 4 major maneuvers: acceleration toward Saturn, deceleration into Saturn orbit, acceleration back toward Earth, and deceleration into Earth orbit. Each maneuver demands massive propellant quantities, and all of it must be launched from Earth at the beginning. The fuel-to-payload ratios required for a crewed round trip with reasonable transit times are so extreme that the mission would require either propulsion technology that does not exist, or a spacecraft so massive that launching it would be impractical. This is not a failure of creativity or funding. It is a hard physical limit. The rocket equation does not negotiate. There is another factor that receives less attention but may be equally significant: communication delay. At Saturn's distance, light itself takes 70 to 90 minutes to travel one way, depending on orbital positions. A simple exchange with mission control, speaking, waiting for your words to arrive, waiting for the response, takes nearly 3 hours. In any emergency, real-time guidance is impossible. The crew must solve every problem with whatever resources and knowledge they must have aboard, and they must solve it before the situation cascades into something unsurvivable. The psychological toll of this isolation is difficult to predict. Humans evolved as social creatures dependent on connection, on novelty, on the possibility of change. Years of confinement in a small space with a handful of other people, no new faces, no new environments, and the knowledge that meaningful help from Earth is physically impossible. This pushes human psychology into territory we have never explored. Studies of Antarctic research stations and submarine crews demonstrate that even much shorter periods of isolation produce depression, anxiety, interpersonal conflict, and cognitive decline. A Saturn mission would extend far beyond any precedent. When all factors are considered together, the conclusion is sobering. Saturn is not like Mars. Mars is extraordinarily difficult but potentially achievable with foreseeable technology. Saturn exists in a different category entirely. The distance is too vast. The energy requirements are too extreme. The radiation exposure is too damaging. The psychological deterioration is too severe. The return journey is mathematically unfeasible without propulsion breakthroughs that remain theoretical. A human being who traveled to Saturn with current or near-future technology would arrive physically compromised by radiation and microgravity, orbiting a world they could never touch with no viable path home. This assessment is not pessimism, it is physics, and physics does not yield to ambition. This does not mean Saturn will forever remain beyond human reach. Technologies that seem impossible today may become routine in centuries to come. Nuclear fusion propulsion could dramatically reduce transit times. Advanced materials might provide meaningful radiation protection. Artificial hibernation could address both the psychological and physiological challenges of long-duration spaceflight. Spacecraft capable of harvesting fuel from Saturn's moons or atmosphere could eliminate the need to carry return propellant from Earth. But none of these technologies exist today. None are close to practical implementation, and none can be assumed simply because we want them. With everything we currently know and everything we can reasonably project for the coming decades, Saturn remains what it has always been, a stunning object in the night sky, scientifically fascinating, visually magnificent, and utterly unreachable for human visitors. There is something valuable in confronting these limits. We live in an era that has grown accustomed to overcoming every barrier. We have climbed the highest mountains. We have descended to the deepest ocean trenches. We have walked on the moon. The narrative of human progress suggests that every frontier eventually falls. But the universe is not obligated to accommodate our ambitions. The distances are what they are. The physics is what it is. Some places may simply exist beyond the boundary of human presence, at least for now and perhaps forever. Saturn reminds us of our scale, of our fragility, of the fact that even our most impressive achievements remain tiny against the backdrop of the cosmos. Perhaps that is not a tragedy. Perhaps it is a reminder to appreciate what we have. This pale blue world where all of human history has unfolded. The only home we can reach and return from. The only place in the known universe where the journey is not permanent. Saturn may be beyond our reach, but what about Mars? Most people assume a Mars mission means eventually coming home. The reality is far more complicated. Watch why the trip to Mars would be just a one-way ticket, to discover why our closest destination might also be permanent.